Good evening again, mga lagan. So we will continue with with the next problem here. Like I said, this assignment was sent by a second year civil engineering student from one of the universities in northern Luzon. And so on this one, looks like he started solving the problem. So the problem is, let me just zoom this out here. Uh, so I hope it is clear. So it says here for the beam with cross section shown, use A equals 25 millimeter, B is 120, C is 150, then modulus of elasticity 200. So this must be a steel section. And determine A, the maximum flexural compressive stress. And then the next one is the maximum horizontal shear stress. Now, in his solution, so he started solving the problem and determine, or at least determine the reaction, and then calculate for the um, or draw the shear and moment diagram. So, um, what I noticed here from this solution, uh, so what I noticed from this solution, this is a trapezoidal load. So this portion here. So this part of the load is a trapezoid. This one. Now in his shear diagram, to calculate for this value x, let's zoom this one here. So he attempted to solve this one, and then I think he got this portion here wrong, because when he solved for x, he used a ratio and proportion, like a linear ratio and proportion. Now the problem with this one is your um load is trapezoidal, so that is a first degree, no, first degree load, trapezoidal or triangular. Like if you divide this into two components, like a rectangular and a triangular load, and then he uses a direct linear ratio and proportion. Now this one here, this is already, the load is in first degree. This is 0 degree, that's fine. So this is 0 degree, the the 40 kilonewton meter, but the trapezoidal load, this is already in the first degree. So this one, you cannot use this equation, this one here, because the load, this line here, this is not a straight line. This is already a curve line, like second degree curve, because your load diagram is already in the first degree. So we will try to solve again this one here, and then we will check. So basically, so the problem is to determine the maximum flexural compressive stress. Now, in this particular problem, we have a cantilever, right? So we have a cantilever. Now, if we draw the elastic curve of this beam, it would look like this one. So assuming that the what we call this one here, the deflection um, is below the horizontal line. And now at this moment, like at zero shear, maximum moment here, right here. So this is our beam. If we exaggerate our beam, and then this is our neutral axis, right? So above the neutral axis, this is in compression, right? So above the neutral axis is in compression. In this particular elastic curve, this portion here between, shall we say, if this is A and this is B. So this one is in compression, and then this one here at the bottom is in tension. Now, if this is simply supported, then all we have to do is just get the maximum moment here and then check for the maximum flexural compressive stress, and that's it. But the problem is we have a cantilever in this at this portion here, at this section of the beam, our elastic or our beam, let's exaggerate the deflection, the curvature, it would look like that one. So again, in this case, this is negative bending. The the section below the neural axis is the one that is in compression. In negative bending, the bottom portion is in compression and then the upper portion is in tension. That's why if you design this, like say if this is a concrete, if this is steel or wood, then that's fine because the stresses is the same. Like it's a mono, like a the section is um like a single type of material. But if this is in concrete, where in tension you rely on the reinforcing bars, that's why above a support, your reinforcing bars, your main reinforcing bars would be at the top if this is a support, at the support location, because this is where the tension is, like above the neutral axis. Now, since we have cantilever, then we have no option but to solve two locations and determine which one produce the biggest flexural compressive stress. So we will again solve for so this one again, he tried to uh, calculate the reaction and then draw the shear moment diagram, but he forgot that the load is already in the first degree, therefore the shear diagram is in the second degree, and you cannot use a direct ratio and proportion, like a linear ratio and proportion. So we will do this one again. So the load is, let's have another page, and then let's just insert the, oh, what happened? It's weird. Oh, okay. So let's insert the picture, insert. Oh, I am not allowed to insert the picture. So insert from files. So this is our problem. So let's do calculate the reaction. So for example, so this is point A. Maybe we'll just draw this again. Let's have a bigger one. Now the load, so this is 40, and then this is 16. So this is RA, and then RB, and then this is 1 meter, this is 6, this is 1, this is 1. So to get the reaction RA, so we will sum up moments at B. So RA, so summation of moments at B, therefore RA is equal to, so 40 times 1, then zero point 0.5, this is 7.5, and then plus, um, so if we project this one here, this line, so that is 16 times 6 plus 1, this is 8, times moment moment arm is 4, and then minus 1, so this is times 3, and then so this plus, so plus the triangle, which is one half of um 40 minus 16 is 24, and then times 6, and then moment arm from B is 2/3 of 6, which is 4 plus 1 times 5, then divided by 8. So RA is equal to plus 16 times 8 times 3 plus 0.5 is 24 times 6 times 5 divided by 8. This is 130.5. So this is our reaction at A. Now, if you are sure with your answer, you can just simply get the reaction at B is the total load minus RA, but we'll just double check, make sure that we have the correct reaction at A. So in order to do that, we have to solve the reaction at B. So reaction at B using the same procedure. So reaction at B is equal to, if you sum up moments at A, therefore RB, sum up moments at A, therefore RB is equal to 16 or 40 times 1 times zero point 0.5. So 40 times 1 times zero point 0.5, and then plus we have the 16 times 8, and then 8 is 4 plus 1 is times 5, and then plus the triangular, which is 1/2 of 24 times 6 times 1/3 of 6 is 2 plus 1 is 3, then divided by 8. So therefore RB is equal to 40 plus zero point 0.5 plus 16 times 8 times 5 plus 0.5 times 24 times 6 times 3. Huh? 40 times 0.5 plus 16 times 8 times 5 plus zero point 0.5 times 24 times 6 times 3 divided by 8, 45.2. 40 times 1 times zero point 0.5, and then 16 times 8, 4 times 5, then 1/2 of 24 times 6 times 3. Right? So 40 times 0.5 plus 16 times 2 times 5 plus 0.5 times 24 times 6 times 3 what's divided by 8. 109.5. And then summation of forces vertical is equal to RB or RA plus RB. It should be equal to the total load. So 40 times 1. Oh, so 40 times 1 plus 16 times 8 plus 1 half of 24 times 6. So this one is 40 times 16 or 40 plus 16 times 8 plus 0.5 times 24 times 6. This is 240 kilonewton. And then RA plus RB is 130.5. RA plus RB is equal to 130.5 plus 109.5. So this is also 240 kilonewton. So therefore, our reaction now is correct. Now, in his calculation, the reaction is actually correct here, which is 130.5 and then 109.5 for the reaction at B. It only happens that when he solved for the moment, like determine this X, um, the reaction or the solution to get the X, he is using a linear ratio and proportion. So let's draw the shear and moment diagram, and then we will determine the value of X where the shear is 0, and that is your location of the maximum positive bending moment. So let's have another page. So let's draw again the um, load. So this is our beam, and then our load. So this is our RA, which is 130.5, and then our RB is 109.5, and then this is, so this is 1 meter, this is 6 meters, 1 meter, then 1 meter, and then the load is 16, and then right here is 40 kilonewton. Now we will draw the shear and moment diagram. So we have here, draw this line, draw this line, draw that line. So let's draw the shear and moment diagram. So we have reaction at A, which is 130.5, and then 130.5 minus 40 times 1 is 90. This is 90.5. And then from here, we have a trapezoidal load. So it would be a second degree curve. So unlike his solution, which is linear, it should be a second degree curve. So the area of the trapezoid is 40 plus 16 and then times 6 over 2. So this is 40 plus 16, then times 3, 168. So this 168, we will subtract this from 90.5. So this is, so again, this is now a second degree curve. So this is minus 77.5. And then from there, you subtract also another, like horizontal load or uniform load, which is 16. So my plus 6 minus 16 minus 77.5 minus 16 is, now this is 1 degree or first degree curve or like a straight diagonal line. Because this is a 0 degree, so this is first degree. So 77, so this is minus 93.5. And then we have RB, which is 109.5. So this is 16. So this is 16. And then 16 minus 16 times 1 is 0. So your shear should start from 0 and finish to 0. So this is your shear diagram. Now, we will solve for the value of x where the shear is 0. Now, you can do like it would be really difficult to do like a, calculation for the area using if this is purely triangular load, then we can use the parabolic equation. But since this is a combination of a rectangle and a triangle, like a trapezoidal load, then what we can do is we will just solve for the value of x so that our reaction at A, so the total load here, the total load within this boundary here, distance x from this line, is equal to the reaction, which is 130.5. So to get the distance x where the total will be 0, like the total shear will be 0, we can do ratio and proportion, but not on the shear diagram, but on the load diagram. So we will do a ratio and proportion from the load diagram. So okay, it will fit. So this is our. We will just we will just draw the portion where it is where the shear here. If you cut section and then you have your moment there, and then this is your reaction at A, right? And then this is your load, which is 40, and then this is 16. Now the distance, this is 1 meter, this is 6 meters. Now all we have to do is to get the distance x, no? Our unknown is basically this one. What is this distance? So that this total of this force is equal to the reaction. Now we will determine what is the equation of this line. Now that line here, if we draw a horizontal line and divide that into a triangular and a rectangular load. So if this is 16 and then the total height here of the trapezoid is 40, therefore, again, this one here is 24, right? So to determine the equation of this line here, 24 down to 16 within 6 meters, you will have to divide 24 by 6. So this is 4 kilonewton per meter like the decrease of your load. This is from 24 over 6. So if you check, so from 40, right? From 40 down to 16, that is 40, then minus 4 kilonewton per meter times 6, right? The total distance so that you will get a 16. So 40 minus 4 times 6, 40 minus 4 times 6 is 16. So therefore, our equation here, this decrease in load, which is 4 kilonewton per meter, is correct. So we have that equation already, or the linear load, like the decrease, the rate of decrease of your load, which is 4 kilonewton per meter. So let's draw that again. Let's draw the load diagram. Oh, so this is A, and then this is B. So this is our boundary distance X. This is our X. So that our total of this area is equal to the reaction. And then this is 4 kilonewton per meter decrease in load. So therefore, if this is 40, this decrease here, this location here would be 40 minus, no, at this location, it would be 40 minus 4 times x, right? This one. Because if x is 6, the total, so the lowest here would be 40 minus 24, which is 16. So this is our height of our like diagram here at this location with respect to x. So therefore RA is equal to 130.5. So the total reaction is equal to the load here uh, until point X, so that the shear is 0. So therefore, this is 40 times 1. And then this area here. So that is plus, the area there is 40, area of the trapezoid, 40. And then the lower one is plus 40 minus 4x, and then times x. Uh, let's write it below here. It won't fit. So this is 130.5 and then equal to 40 times 1. We are summing up the forces vertical so that the total is 0. Because this at this point x, the shear is 0 based on our shear diagram, right? So I hope you can follow. So this is plus 40. This is the trapezoid now. 40 plus 40 minus 4x. And then our distance is x, and then 1/2 of that, right? So if you have a trapezoid, right? If you remember that one, if this is A, and then this is B, and then this is distance x, our area is A plus B times x, and then times 1/2. So this one here, basically. So we'll erase this. So that one. So we already equate this reaction versus the area here, so that the total is 0. So this is our equation, this one. Now we will solve for x. So we will simplify this one. So this is 130.5 is equal to 40, and then plus this one is plus. Oh no, we have another bracket here. That one. So 40 plus 40 is 80 minus 4x and then x over 2. That one. Because this is our A and then this is our B. So 80 minus 4x, and then again 130.5 is equal to 40 plus 80 times x over 2 is 40x. 4x times x over 2 is 2x squared. Now rearranging this one, we will have 2x squared minus 40x and then plus 130.5 minus 40 is 90.5, and then this is equal to 0. So this is a quadratic equation. Now we have two values. With this one, it is quadratic equation. Then we have two values of x. So we have x1 and then we have x2. Now we can use the quadratic formula, but we'll just use calculator to make it short or faster. So 3. So A is 2, and then B is minus 40, and then C is 90.5. So X1 is 17. No, X1 is 17.4, and then X2 is 2.6 meters. Now, obviously, this one, our span is only 8 meters, but X1 is 17.4. Therefore, our location of the zero shear is at 2.6 meters. So this one, you disregard this one because that is too much. 70.487 larger than our span. So our location of zero shear is 2.6. Now, with that in mind, we can now solve the moment at this location. So like I said, we can solve this using the area of this curve here, but to be honest, I don't even know how to calculate this one. If it's a regular triangle, then I can for sure. But if it's a trapezoid, um, I could probably solve it, but I never did it. Even like when I was still a student. So what I will usually do, and even our professor, when I was still at the St. Joseph College in Masin, the solution for this one is just in locating for the zero shear. If it is complicated, just sum up the forces vertical, and then determine the distance x where the reaction versus the load is 0. So you don't have to solve for I mean, you can probably, but why would you punish yourself? So again, so we already have the location. So we have, oh no, uh, so we have here 40 and then down. So this is our 130.5 um reaction at A, and then now we will cut the section. So um this is 2.6. So this is 2.6, and then this is 1, and then this is your shear, and then your moment. So this is 40, and then this one, um we have 4x right? The equation is 4x, so 40. So 40 minus 4 times 2.6, we have the value here is 29.6, right? 29.6. So if you want, we can check if that is really correct, right? 40 times or 40 plus this area is equal to 130.5. But we already solved that value of x based on that equation anyway. So that should be the correct one. So to get the moment here, right? So when you cut section at zero shear, right there, you sum up moment. So moment there is, so moment is equal to 130.5 times 3.6, and then yeah, 3.6, then minus 40 times 2.6 plus 0.5, 40 times 1, 40 times 1, then moment arm is 2.6 plus 0.5, 3.1, and then minus the trapezoid. So we can, if you want, you can divide this one here. So this is 29.6. So if that is 40, 40 minus 29.6. So this one here is 10.4. So minus 29.6 times 2.6 times 1.3, and then minus the triangle, which is one half of um, 10.4 times um, 2.6, and then the moment arm is what, 2/3 of 2.6. So moment there would be 130.5 times 3.6 minus 40 times 3.1 minus 29.6 times 2.6 times 1.3 minus zero point 0.5 times 10.4 times 2.6 times 2 times 2.6 divided by 3. So this is 222.32 kilonewton meter. So this is the positive moment. Now to get the negative moment right here, the negative moment, if you cut section at the cantilevered portion, if you cut section, so this is your cantilevered portion, right? So this is 16 kilonewton per meter. This is 1 meter. This is your RA. This is your, or not RA. This is shear at B. Not the reaction at B, but the shear at B. And then the moment, now this is negative moment. So therefore, negative moment is equal to 16 times 1 times zero point 0.5, which is 8 kilonewton meter. Now, if you look at the difference between these two, it's just like 8 versus 222. So most likely, what will govern when finding the maximum compressive stress is the positive bending. I mean, we could solve, right? So if this is our section, but because this is irregular, your moment of, or your neutral axis should be closer to the bottom because this is thicker. This area here is thicker than this one. So when we solve for the maximum compressive stress here, which is if B is equal to MC over I, now this time we cannot use the 6M over BD squared because this is a hollow rectangle section. So MC, now to get this compressive stress here due to flexure, your C here would be this one because at the support location, this is where your compression. And then in the middle, in the midspan, or not really midspan, but at the zero shear, like positive bending, that's the time that if we use this bending, our distance C would be this one. This is for positive moment, and then this one is for negative moment. But because of the difference, 222 versus 8, then we will just use directly this one. I mean, we could solve for at the support location, but considering the difference between the moments at the positive moment versus negative moment is just too much, so we'll just disregard this one for now. If it is too close, like for example, this is 222 and then this one is 200, then it's possible that the maximum flexural compressive stress is at the support location, like this one here at the bottom. So we already have the maximum moment. Now, to get the maximum flexural compressive stress, then we will solve for the moment of inertia because um if B wait from if B is equal to MC over I, now we have to determine the distance from the neutral axis to the outermost compressive fiber and then the moment of inertia as well. Now, since it is irregular shape, rectangle, like hollow rectangle, let's see, check what's the dimension. A to A. So, uh, so our section, so our A, just assume that that is perfect, like this one here. This one here is equal on that one. Or we'll just do that again. So, so the bottom portion is thicker, which is 2 times A, and A is 25. So this is 25. This is 25. And then this is also 25. But this one is 50. Because that's twice this one is 25. That's twice the thickness A. And then B, the width is 120, then total depth is 150. So this one here is 120, and then this one is 150. Now, by observation, this one here is thicker than the one at the top. Therefore, our neutral axis would be closer to the bottom. Now, what we will do is we will divide this area into four separate section. So we will divide it here. So this one would be our area 1, which is the same as this one here. And then this is our area 2. And then this is our area 3. Right? So area 1. area 1. So this is area 1, area 2, area 3, and then this is area 4, which is equal to area 1. So area 1 is equal to area 4 is equal to 150 by 25. So this is 150 by 25. So 120 by 55 is 3750. Then area 2 is, so if this is 120 and then minus 50, that is 70 times 25. So area 2 is 70 times 25 is equal to 1750. And then area 3 is the one at the bottom, which is 70 times 50 is equal to 70 times 50 is 3,500. Therefore, area total is equal to area 1 plus area 2 plus area 3 plus area 4. So area 1 plus area, which is equal to area 4 is 3750. 3750 times 2, because there are two area, oh no, not equal, plus 1750 plus 3,500. So the total area is 12,750. I guess this is in millimeters squared, I think. Yeah. 12,750 millimeters squared. So we already have the area. Now, to get the moment of inertia, we will get also because we will be doing a transfer moment of area, so we will calculate for the centroid of its area, right? So if that is area 1, so area 1 would be, say this is our datum line. So area 1 would be the center of this area, that one. So this is our y1, no? That is our y1. X1 will be just at the middle because it's symmetrical on both sides, but top and bottom it is not symmetrical. So we'll just calculate for the location of the x, the part x would be right here at the center, but the neutral axis, like the horizontal, like the barred y, it would be closer to the bottom. So we will that one. This is y1, and then this is y2 here at at the middle here. This is y2, and then this is y3 at the middle. So y1 is equal to y4 because that is the same area. So this is 150 over 2, which is 75. Then y2 is equal to, y2 is the one area 2 above, right? Yeah, so this is the 150 minus, so this is 150 minus 25 over 2. So this is 137.5. And then y3 is 50 over 2, that is 25. So we already have that one. Now to determine the distance from the neutral axis, or let's solve the location of the neutral axis now. This is barred y. So therefore, will it fit? Yeah. So area total times barred y is equal to area 1, y1 plus area 2, y2 plus area 3, y3 plus area 4, y4. So therefore, barred y is equal to area 1. Area 1 is 3750 times y1, which is 75. And then since this is equal to y4 or area 4, we'll just multiply this by 2. So this 2 is because we have the same area 1, which is equal to area 4. And then area 2 is 1750 times y2, which is 135.5, and then plus area 3, which is 3500 times y3, 25, and then divided by the total area, which is 12750. So barred y from the bottom, no, the location of the neutral axis from the bottom of the suction is 3750 times 75 times 2 plus 1750 times 135.5, yeah, plus 3500 times 25 divided by 12750. This is 69.578. So let's say 69 point, we'll just use 69.8 millimeter. There will be, although it is not advisable to round off while you are still in the process of calculation, because it might be a large difference in the end. Um, During board exam, do not round off your value until it is the final answer. So, for the sake of discussion, we'll just round it off to 69.8 from the bottom. So this is the location of the. So again, um, our section. This is our section, right? So the center of the diagram, or the center of the height, would be, see, this one 50, this is 75. But since this is thicker, this portion here, that's why our neutral axis is closer to the bottom. That's why instead of 75, if this is like a symmetrical, then of course your neutral axis would be at the center of the mass. But since we have thicker section at the bottom, then our location of the neutral axis is 69.8. So 69.8. Now this one, say if since we are using the if you remember, we have this is our diagram, right? And then our elastic cord is this one, that one. Now the moment here is really small compared to this one. That's why we decided to just calculate for this one. Although if the moment value is close, like the positive and the negative moment are close to each other, like the value itself, just disregard the sign. The sign only indicates like which one is compression, which one is in tension. But the value is or the when you say maximum moment, just get the absolute value between the two, and then whatever is the biggest one, that's your. In this case, this is the biggest one is the positive bending. Then we'll use that one. So in this location, the one at the bottom or at the top of the neutral axis are the one in compression, right? Are the one in compression. So therefore, we will be using this value of C, because in the definition, MC over I, the C in that equation is um, the location of from the neutral axis to the outermost compression fiber, not the tension. Because if this is in concrete, the only reason why we calculate for this one, like the difference between the two, or not really just because it is concrete, but it is important in concrete design because that would dictate where the main rebars would be, right? So if it is positive bending, uh, if you remember, concrete is really good in compression but really weak in tension. That's why we have to provide steel reinforcement at the weak portion of the concrete, which is the one below the neutral axis. If it is in positive bending, positive moment, the one below the neutral axis. That's why at midspan, our rebars for concrete are always at the bottom, and then near the support. If it is rigid connection, of course, you only see a simply supported if in the case of a like a bridge, like a girder, where you have the pin connection and then you have the roller connection at the other end. But in a regular building, like if it is a building, um, unless you are using a precast, then for sure. But the conventional framing, which is beam column like rigid connection, the the negative bending at the support. That's why at the very support, So if you have this beam, and then assuming this is a rigid connection here, the rebars at the near the support, this is the point of inflection. This is L over 4. This is where the change in curvature. This is L over 4. This is L over 2. So the rebars right here is at the top because this is in tension here. This is in tension. This is in compression. And then this one at the center, the change in right here at L over 4 change in curvature. This one will be now in compression. This is now in tension. That's why the rebars at the bottom or at the midspan is right here. And then again, going back to your main rebars at the top because it is a negative bending. So we already have that uh, distance from the axis at the bottom. Then therefore C is 150 minus 69.8, which is 150 minus 69.8, 80.2 millimeter. So that is our distance. Now, to get the moment of inertia, no, to get the moment of inertia, we will transfer we will get the distance 1, distance from the neutral axis to the center of the segment. So D1 is equal to um, D1 is equal to barred Y. Actually, that is the barred Y minus um, Y1, and then take the absolute value. So, or you can just directly, for example, this one here, the center is at the top, so your distance would be above the um, neutral axis. But you can use this formula here, barred Y minus Y1, and then just get absolute value. If it is positive, therefore your distance 1 is below the neutral axis. If it's negative, then it's above the neutral axis. That means the y1 is bigger than your barred Y. So that one, our barred Y is for area 1 is 19 or 69.8. Then minus y1 is how much? 75. So 75 minus 75. Therefore, this one is equal to 60, 69.8 minus 75. This is minus 5.2, or therefore it is above the neutral axis. And then, regardless of this one, when you do the transfer moment of inertia, B will be squared anyway. So even if it's negative, that would still be positive. So we'll just leave it like that. So for now, and then D1, and then this is equal also to D4. D4 is also minus 5.2. So don't be confused with the negative sign. It only indicates that the distance is above or the center of um, the segment is above the neutral axis. And then D2, again, absolute value of bird y is 69.8. Um, uh, 69.8, and then y2 is 135.5. 135.5, and then absolute value. Or you can just disregard the absolute value. Even if it's negative, um, when we square the distance, that would still be positive. So 135.5 minus 69.8. So this is 65.7. And then D3 would be bird y is 69.8 minus D3 or Y3 is 25. So this is the only time where your distance is positive just because your bird y is bigger than your centroid or distance of your centroidal distance of your sub area, I would say. So 69.8 minus 25 is equal to 44.8. So that distance 44.8 is from the center of this area, going up to the neutral axis. So we will now solve the transfer moment of inertia because it is a hollow section. Now I is equal to, right? So this is the centroidal moment of area plus, or centroidal moment of inertia plus area times d squared. So this is our general equation for transfer moment of inertia. Now, if it happens that the moment of inertia of the overall, like the total moment of inertia is not located at the centroid, so that's why you have to do the transfer moment of area. So for I1, right? So for area 1 and area 4, because that is equal to area 4, this is bh cube over 12. So b is 25, right? So this is 25 times 150 cube over 12, then plus area, which is 3750, 3750 times what is d1. D1 is 5.2, oh no, yeah, 5.2 squared. So again, this is negative, right, when we calculate this one, but since this is squared, then it doesn't really matter at this time. So area 1 plus area 4, like the moment of inertia, this is not area. So this is moment of inertia of 1 is equal to moment of inertia, or yeah, 4. So this is 25 times 150 cube divided by 12 plus 3750 is 5.2 squared. So this is 7132650 millimeter to the fourth. And then we now have the I3. So I3 is equal to dh cube. I3 is what is our I3 or I2, not I3. I2 first. So I2 is 120 minus 50, that is 70. 70 times 25. Now our B is 70 times 25 cube over 12. And then plus area is 70 times 25. Area 2 is 1750, right? 1750 times distance 2, which is 65.7. 65.7 squared. So again, if it's negative, it doesn't matter because you will square that one, then that would be positive. Cube divided by 12 plus 1750 times 65.7 squared. So this is so this is 764 5003.33. And then lastly, our I I3. So I3 70 times 50 cube over 12 plus 3,500 times how much is our D3? 44.8. 44.8 squared. So therefore, our I3 is equal to 70 times 50 cube divided by 12 plus 3,500 times 44.8 squared. This is 7,753,806.667. So therefore, our total moment of inertia is equal to I1 plus I2 plus I3 plus I4, where I1 and I4 is the same. So therefore, kana plus I2 plus 764 5,003.333 plus 7132,650 times 2. Our moment of inertia total is 2966410 millimeter cube. Oh no, millimeter to the fourth. So we already have, so the maximum flexural stress FB is equal to MC over I. We already have the moment, we already have the C, we already have the I. Then we can just simply substitute that one. M is equal to, how much is our M? 222.32. So this is 222.32. Now this is in kilonewton meter. So we will convert that into, it's either we'll convert the C and the moment of inertia to meter, or we'll just simply convert the moment from kilonewton meter to Newton millimeter. So this is times. So Newton to Newton times 1,000, then meter to millimeter times another 1,000, and then, oh, it won't fit now. And then times your C. Your C again, that we are positive bending at the center, or not at the center, but located near the center of the beam. Then we will use the upper distance from the neutral axis to the outermost compressive or compression fiber. So which is this one, 80.2. So times 80.2. So this is our C, and then divided by the total moment of inertia, which is 29,664,110. Therefore, our maximum compressive bending stress is 2.32 times 1 million, 1,000 times 30 times 80.2 divided by 296,64110. So this is 601.06 um, Newton millimeter. So this is in megapascal. So I don't know if this is maybe during calculation we probably, because this is quite a high um, bending stress. So I don't know, but the procedure is what I've shown you, like the procedure. That is the procedure on how to calculate this one. So maybe that's the actual. I don't know because we cannot compare the the answer because we don't have the what we call this one. We don't have the answers below, like the choices. Um, if we have choices, then we can definitely check our answer if that is um, in the choices. But since it's not included when he sent this picture for this problem, then we will just assume that our values are correct. In a way, if it is, the answer itself is wrong, but the procedure, that's how you calculate for the maximum compressive stress. So again, if ever the moment at this location the moment at this location is really close to the moment at the support, then you have to do another calculation where you use the C below the neutral axis for the negative bending. But since the difference, like imagine the negative bending is only 8, but the positive bending is 222. So that's like the difference is just too high. So we'll just disregard the negative bending. Now, for the maximum horizontal shear stress, like letter B, maximum horizontal shear stress, our general equation for the maximum shear stress is, our general equation is, if V, the shear flow is V times Q over IB. So V is your maximum shear, Q is your first moment of area, and then we already calculated this one, and then B, I mean, from the diagram, from the cross section, we will be cutting at this section here. So therefore, our B would be, because our neutral axis is right there at 60, was that 65.7 from the neutral axis, from the bottom. So B would be 25 here, 25 plus 25. So our B is 50. No? So we have B is equal to 50, and then we already have the I, which is how much? Our I is, total I is 296,64110. 296,64110. And then our V, now we will look at our shear and moment diagram. Where is it? Right here. Now, our maximum shear. So on the left reaction, we have 130, and then our reaction at B, no, our reaction at B, that's not the shear at B, because the reaction at B is the combination of the shear to the left of B plus the shear to the right of B. So when you design, for example, this section here, when you design for the shear reinforcement at this location, you only use the 16. And then left of B would be 93.5. So, for example, if you have the beam now, we'll cut here, and then so this is our reaction at B. Now the spacing here, because this is smaller, would be say uh 75 or 100. But at the left of B, your shear is 93. So it is expected that the reinforcing bar or the shear reinforcement at this location left of B would be closer than the cantilevered portion. But since although 16 plus 90, it's still lesser than 130, but just in case the total reaction at B is higher than reaction at A, um, in this case, whichever is higher, like this is the actual shear values here, not the total reaction at B. So in this case, our maximum shear is 130.5, which is the um, reaction at A, 130.5. So 130.5, and then this is in kilonewton times 1000, that is 130 and then 500 Newton. So this is millimeter to the fourth, and then this is millimeter. So the only missing one is uh, our Q, the first moment of area. Now, the first moment of area, we will determine it's either from the top of the neutral axis or from the bottom of the neutral axis. So, so let's go back to our section. So our location of the neutral axis is right here, which is how much? 69.8. So we'll see. We will use the one at the very top. So we'll use this one. We'll use that one and then this one as well. So this is our one, this is one, and then this is two. Or one, two, three. Where one and two is equal. So Q1, so this one. So if this is 69.8, this is 150. What's the difference again? Um, 80.2. So 80.2. So this is 80.2. So therefore, our Q, this one is area, first moment of area of this section is 25. Q1 is equal to Q2, which is 25 times 80.2 times 80.2 over 2 times 80.2 over 2. So Q1 is 25 times 80.2 squared times 0.5. This is 81003.125. And then Q3 would be area of that one is 70 times 25, and then 80.5, 80.2 minus 12.5. So 70 times 25 times 80.2 minus 12.5. This is 118475. So the total Q above the neutral axis is 81003.125 times 2 plus 118475. So this is 280481.25. We'll see if this is the same if we use the bottom one. It should be the same. If it is not the same, then there's something wrong with our equation. So Q1 and Q2, or the bottom portion, so again, Q1 is equal to, the bottom portion is 69.8 times 25 times 69.8 over 2. This is also equal to Q3 or Q2. So this is 69.8 times 25 times 28 times 0.5. So this is 6900.5. And then there must be something wrong, but this is too big. 70 times 25 times 80.2 minus 12.5. Then plus 25 times 80.2 plus 80.2, 279. 25 times 80.2 squared 0.5 times 2. Well, it's not the same. 25 times 80.2 plus 80.2 times 0.5. This is 8,000, 80,400.5. So this is 80,400.5. Then times 2 plus 1184 is equal to, this one is 279,276. And then on the other one, 69.8 times 25, 8 times 25 times 69.8 times 0.5, 6, oh, sorry, 60,900.5. And then Q3 would be 70 times 50 times 69.5 minus 25. So 70 times 50 times 69.5 minus 25. So this is 155, 750. The total plus 6900.5 times 2 is 277,551. What's the other one? 277. Oh, so right here, 279, and then right here on the other one is 277. So like I said, this is probably due to the rounding off of the location of the centroid. I mean, like I said, it's in millimeter, and then if you change like 1,000 times, whatever is the, or 1 million times, the whatever's the rounded off value, that's a lot. So I mean, this is really close, 277 versus 279. So it's probably just the rounding off, but it should be the same. No? So the when you calculate for the maximum shear, determine the location of the neutral axis, and then for the Q, it's either use the upper portion or the lower portion, and that should be the same. So so the final answer would be the maximum shear is it's equal to VQ over IB. V is how much was that again? Our V is 130,500. This is 130,500 times Q is 277. We'll just use that one. 551. And then the moment of inertia is 296,64110. 296, 296,64110 times B, which is 50. So the maximum horizontal shear is 130,500 times 277,551 divided by 296,64110 times 50. So this is 24.42. This is Newton millimeter, so this is mega Pascal. So again, we cannot compare this value because we don't have the choices. Um, when he forwarded the question, there were no choices included. So we'll just assume that this is correct value. But like I said, the procedure is what I showed you. That is the procedure to get the maximum flexural compressive stress and the maximum horizontal shear stress. So to the student who send this question, I will just not name names. So I hope this clarifies. This will help you for your exam this Saturday. And we still have like few. Um, oh, it's already 1.5 hours. So imagine this problem alone is 1.5 hours. So again, the next question I will try to, if I have time tomorrow, I will um, continue solving the question for tomorrow, like the remaining questions. He actually sent me a couple of or a handful of questions, but the other question was deflection of a beam using double integration method. So we will probably focus on that tomorrow if I have the time, um, because that would take time also to solve. So I hope this will help you a lot. And again, I will post this in my video in my YouTube and Facebook page, and hoping that this would um, reach everybody, like all the students back home in the Philippines, and this will help you in your studies. So again, um, please subscribe to my channel, and if you have any questions, just send it to me or just write in the comment section, and then I will try to answer as quick as I can. And bye.